Hi guys. In this lecture we're going to talk about multi-level paging. Hopefully this will be a quick one. So recall single level paging. We had our logical address space and we were able to, based on the virtual address that was generated by the CPU, we were able to take this address, look into a page table, and in the page table it told us the frame number, and so we could see where it was at in the physical space. And details of this were that each one of the addresses had a page number, so they had a portion that was dedicated to the page number, which would allow it to index into the page table. And there was an offset that would tell it where in the actual page it was sitting. So here, this would have an offset of 0, 1, 2, 3. Right? So this was single level paging. The issue with this was that these page tables can get really, really big. So this was an issue. So page table size. So last time in the paging introduction, we have one example, and that one ended up to be a 512 gigabyte size paging table. And remember, these page tables have to sit in memory, and that's a lot of memory to take up. So the solution here that we decided was multi-level paging. So now instead of having a single page table, we're going to have multiple page tables. And the way that this will work in the address is that now, instead of just having this one P here that would index into one page table, so we're going to keep the partitioning the same, the offset will still remain the same, but we're going to spread this out into maybe a P1, a P2, and the scales, of course, so this is just a 2-level page table, but it can be n-level, really. So we could end up splitting all into a bunch of different ones, ... P of n, and D remains the same. So each one of these P's here is going to index into a different level of the page table. So the first one is going to be index into an outer page table. Inside here it's going to have the index, or this one is then, the second one is then going to index into a second page table, kind of like, sorry, that's misleading, but the second level is going to have a bunch of different page tables, and each one of these is going to be connected to each one of those. Okay, so let's look at some examples. So here we have, this is a 2-level page table, and we have two different page numbers, P1 and P0, and so we address into our first page table, and that's going to allow us to access into the second page table, see where we need to be in P2. So this is going to tell us which page table, this is going to tell us which page table to go to, because there are going to be multiple page tables here. And then this P2 is going to tell us where to go into that page table. Okay, so then the physical address is going to be kind of a big conglomeration of these page number and offsets. So these are all going to add together to finally become the physical address. So let's talk about how this saves space. So imagine that we have a virtual address that has a page number, has 4 bits associated with page number. So we can use 4 bits to index into a page table. So how big is our page table going to be? So our page table, if we have 4 bits to address into it, we can have up to 2 to the 4 entries. So this is 16 entries. So here I'm going to draw our page table. So this is going to be our single page table. It can have 4 to the 12 or 2 to the 4 entries. So this is 16 entries. Okay. So now if we move to a 2-level page table, we're no longer going to have this address. We're going to split our address into a P1 and a P2, And now we're going to have, so it's still going to be the same number of bits, so we have to split our bits. So we'll say this is 2 bits, and this is 2 bits. So now since that P1 only has 2 bits, now in that first page table, which we're going to call the outer page table, we can only have 2 to the 2 entries, or 4 entries. So now each one of these entries is going to have an associated second inner page table. So let me draw those. So each one of these is going to have an inner page table. Draw that one out there. And we have 2 bits to address into that one, so they can also have 4 entries each. At this point, you guys are thinking, okay, wait a second. So our single page table only had 16 entries, and now it looks like we're going to have 4 more, right? We're going to have the original 16 here in our outer tables, or inner tables. And then we're also, so this is going to be 16 entries. And then also we have this outer table. So this is another 4. So that's 20. That's more. So that's not what it's supposed to be. So that we're supposed to save space with this, but we're not seem to be saving space. So where does the space saving come in? So the space saving comes in this sense. So this 2-level page table, it maps all of the physical memory, and that's not completely realistic. So there's going to be some parts of your physical memory that you're not going to use. It's going to be blocked off. So maybe you can't use this part, you can't use this part, and so, or maybe that's where, you know, your page table is sitting, or something like that. And so you can use this information that these spots of memory are never going to be used. So let's say that this corresponds to these entries here. So these are never going to be used. So now you can go ahead and just completely block off this entry. You're not going to use it, so you don't need it anymore. So you don't even need to map it. You don't need to put it in your table. And let's say that this spot here corresponds to here. And so now you can block off this entire space. This is usually what happens. This is usually the scenario where in the overhead of these multi-level paging, if you look at it theoretically, they do end up using a more space. However, because you can make these kind of, you know what memory is blocked off, what spots of memory you're even allowed to write to, you can end up saving yourself space in this sense. You can block off these entries, and now you end up having to use a whole lot less space. So this is usually how your memory looks. It's a little bit more sparse. If we had a single page table, we don't have control over that. We just have all of the memory areas marked. So similarly to the paging example, I'm going to ask a few more questions that are going to be similar to homeworks and exams. So the first question I'm going to ask, so we're back to our original machine that we were working with last time. We have a 64-bit machine, 16 terabytes of RAM, and a 4 kilobyte page size. So my first question is, assume a 2-level page table. The outer page table has 16 4 kilobyte pages, with each entry being 8 bytes long. How many entries can this 2-level page table system contain? Okay, so how many entries can we map out here? So it's pretty straightforward. So the first thing that you have to figure out, so this is your outer page table. First thing you need to figure out is what's the size. And we'll do it in terms of bytes. Okay, so the outer page table, so we know it has 16 4 kilobyte pages. So 4 kilobytes, we remember this from last time, I'll do it one more time. So 1 kilobyte is equal to, you want to move all these into the powers of 2, so it is equal to 2 to the power of 10. So we have 2 to the power of 10 times 4. That's what 4 kilobytes is. And so this is 2 to the power of 10 times 2 to the power of 2, which is 2 to the power of 12. And then 16 is 2 to the power of 4. So we have 2 to the power of 4 times 12. Well, see, this is why you guys, see, you're not doing your job. Okay, so not 12, 2 to the power of 12, which is equal to 2 to the power of 16 bytes. Okay, so that's how big this space is here. We got 2 to the power of 16 bytes. But that doesn't exactly answer the question. The question is how many entries. So to figure this out, we need to, so each entry is going to be 8 bytes long. So we need to take 2 to the power of 16 and divide it by 8 bytes. And 8 bytes is 2 to the 3. And this is going to be equal to 2 to the 13. So this is 2 to the 13 entries. Okay, that's how many entries we can have in here. Okay, so the question that follows is how many bits are needed in order to index into that outer level page table. So we know from the last question that this has 2 to the 13 entries. So how many bits are we going to need to be able to index into each one of those entries? Not a trick question. 2 to the 13 entries needs 13 bits. Right, so you take the power, that's the number of bits needed to represent that many entries. Pretty straightforward. Okay, here's another question. If 34 bits of the virtual address are used to index into the inner page table, how large is the virtual address space? Okay, so let's draw out what we have so far. We have our outer page table, which had, 2 to the 13 entries? Okay. We have our, so 2 to 13 spots, and now we have 34 bits of virtual address are used to index into the inner pages. So that means that each one of our inner pages can have 2 to the 34 entries. Right, because we have 34 bits that can represent this, so we can go 2 to 34 spots in this. So that each one of these has 2 to 34 entries. Okay. Inner. Okay, so the final question is we have our virtual address space. So how large is that going to be? So if we have how large can it be is really the question. So if we have all of these possible places to map, then we have up to, we'll stick with green, 2 to the 13 times 2 to the 34 possible entries. So there's all possible combinations of these virtual addresses of how they can address in. Okay, so this is going to be equal to 2 to the 47th. Okay, so that's the number of entries, but that's not the question. The question is how large. Okay, so we know that the virtual address space is in pages, right? And each one of these pages can index into this many number of entries. Okay, so that's the total number of pages that we can have. So to get, here, let me do that. To get the total size of the virtual address space, we just need to multiply this by the page size, right? We know the page size. So the page size is, let me erase this. the page size is 4 kilobytes, which we've already done a bunch of times. We know that's 2 to the 12th. And this is going to be 2 to the 59th bytes. All right, so that's going to be the size of the virtual address space. All right. So that's multi-level paging. Of course, all of this can scale to many, many more number of pages. And in fact, that's how most modern computers are set up, to have these multiple paging. So next time we're going to talk about the translation look-aside buffer and how that can speed up this paging process. Thank you. Let me know if you have any questions.